All right, so we're going to turn our attention to liquids specifically. We've been talking about gases, and then we're talking about intermolecular forces, which obviously have to do with all phases. But we're going to look specifically at some things that have to do with liquids. We'll start with some concepts that you already know, but you're going to be able to understand a little bit better now that you understand intermolecular forces, and that is the idea of vaporization and condensation. First of all, vaporization and the word evaporation are the same thing, okay, just so you know. So evaporation, vaporization are the same thing. You can use those terms synonymously. But we know that vaporization is when we have a liquid going to a gas. A liquid going to a gas. So that's how we've always defined vaporization. But what we need to remember and what we need to think about is the fact that a liquid going to a gas, now that we understand intermolecular forces, means that we must be breaking some sort of intermolecular force to be able to become a gas, because gases have much weaker intermolecular forces than liquids. So what's really happening with vaporization is that particles that are at the surface of the liquid, first of all, this is happening at surface liquid molecules only. This little guy down here at the bottom, he can't evaporate. He can't do this process because he's not at the surface. So in order for vaporization to occur, the particle has to be at the surface. And then it also has to have more than the average amount of kinetic energy of the particles that are in that container. So what does that mean? Well, first of all, we know that temperature is a measurement of the average kinetic energy of our particles. So these particles have some sort of average kinetic energy based on what their temperature is. But just as the word average tells you, it means that some particles are moving faster and some particles are moving slower. So up here at the surface, I'm going to have a lot of particles. Some of them are going to have a lot of energy. Some of them are only going to have a little bit of energy, depending on which particle it is. The ones that have more than the average amount of kinetic energy will have enough energy to break the intermolecular force. Remember, there's another particle here trying to hold on to it, another particle here. It can break that attraction that it has for those other particles, and it can go up here and become a gas particle. Okay, whereas maybe this one right here isn't moving very fast. This guy right here, he might not be moving very fast. If he's not moving very fast, then he's not going to be able to do this. He's not going to be able to escape. He's going to be held on by these other particles down here. Maybe this one's moving really fast. He can break the attraction that he feels for those particles down there, and he can get out of town. And so that's what's happening with vaporization. And that's why a liquid doesn't just completely vaporize within seconds of being in open air, is because not all the particles can do this. Only ones that have above average kinetic energy are going to be able to do that. Now down at the bottom, you see, I'm trying to move this so you can see it better. You see a little note here that says molecules with weaker intermolecular forces evaporate more quickly. I want you to think about that for a second. Molecules with weaker intermolecular forces evaporate more quickly. Remember, we said to evaporate, this particle has to have more than an average amount of kinetic energy so it can leave, and it has to break its intermolecular force. Well, the weaker those intermolecular forces are, the easier they will be to break. Okay, so things that have low or weak intermolecular forces are going to have lower points at which their temperatures at which they start to evaporate. That's why if you leave like a bottle of rubbing alcohol open overnight, it will evaporate a lot quicker than if you leave a water bottle open overnight. Okay, so that's the idea of evaporation. It's going to be really important in what we're going to be talking about today. The opposite process is called condensation, and this is when molecules will liquefy back from the gaseous state, right? Condensation is when we go from a gas to a liquid. So what happens here is you might have some particles that have evaporated and they're hanging out at the surface of the liquid, and a particle might get too close to the surface and might be a pretty slow moving particle, and as it travels past the surface, these surface particles in here, they pull it in. They actually attract it back by those intermolecular forces. Now that can only happen to really slow moving particles that are at the surface of the liquid, but if they're moving slow enough, then the attractive forces within the liquid can pull them back in. Okay, and so that's the idea of condensation. Really, the evaporation and condensation are going to be concepts that we are going to need significantly in what we're going to be discussing. Now, the main topic for what we're going to talk about today is something called vapor pressure. Okay, vapor pressure. Now, vapor pressure, as the name infers, is the pressure of a gas, but it's a really specific situation that we are talking about. And before I can explain vapor pressure to you, you have to understand something called dynamic equilibrium. So what dynamic equilibrium is, well, actually, let's just look at this first beaker. So this beaker here is open. Okay, so we said there's particles at the surface. Some of them have enough energy to overcome their attractive forces and evaporate. So we're going to have some particles that are going to be going off into the world. Now, if we have an open container like this, if you think about it, the particles aren't going to stay here because gases like to spread out. So these particles are going to leave this area. Okay, they're going to diffuse. If we have an open container, really it's diffusion. They're going to diffuse out, okay, and go away from the surface. But in the second beaker, my very poorly drawn picture here, you can see we have a lid. Okay, this is a closed container. And we can only end up with a system of dynamic equilibrium if we have a closed container. So what's going to happen here, same thing as before. I put the lid on. As soon as I put the lid on, some of these particles that are here at the surface of the liquid are going to do their evaporation, and they're going to become gases. Okay, and that's going to happen for a while. But this time, those gas particles can't leave. They're going to be stuck up there above that liquid. And so what's going to happen is you've confined the area by which those particles can be. So you might start getting a buildup of particles up here. But what's going to happen is every once in a while, one of these slow-moving gas particles is going to get too close to the surface of the liquid. What did we just say happens if a gas particle gets too close to the surface of a liquid and it's moving slow? That's right, it's going to get pulled back in. So the particles are going to start to get pulled back in, and at the same time, particles are still going to be exiting and going back into the gaseous state. So we're going to have this sort of exchange of gases becoming liquid and liquid becoming gas. And after some amount of time, it is going to equal out. So you're going to have maybe 3 liquid particles becoming gas particles at the exact same time as 3 gas particles are becoming liquid particles. Once it has equaled, once those rates are the same, then we are at dynamic equilibrium. Take a look at this definition. It says when the rate of vaporization, so that's the particles going out, and the rate of condensation, particles going back in, are equal, you have this system in dynamic equilibrium. And it only can happen in a sealed container. Okay, once we take the top off, the gas particles will all disperse and everything gets messed up. You put the top back on and eventually it will reach this state of dynamic equilibrium. So like the water bottle you might have sitting on the desk next to you right now. If it's been sealed for a couple of minutes, that liquid that you see at the top has actually is evaporating and going into that open area up top, and up top there's actually gas particles that are recondensing, and if you leave it closed for long enough, you're going to end up with this dynamic equilibrium situation in your container. Okay, so in order to look at vapor pressure, we have to be in a system of dynamic equilibrium, and that's why it's important for us to have that concept there. So the rate in the forward direction is equal in the rate in the reverse direction. So gas becoming liquid is going at the same rate as liquid becoming gas. And so net, you don't have any different change in how many particles you have, but they're still interchanging continuously. Now, what does this have to do with vapor pressure? Well, let's see. Okay, so back to this slide. Sorry, I didn't realize I didn't have a different one. So what vapor pressure is it's the pressure, let's see how I want to do this. It's the pressure up here, okay? The vapor pressure is going to be the pressure that we have. I have no idea what is going on here. Computer doesn't like me. So the vapor pressure is the pressure of the gas above the liquid. Okay, the pressure of the gas above the liquid, but only once dynamic equilibrium has been achieved. Okay, and it's okay that it's still exchanging. The rate of evaporation, rate of condensation are the same because we'll still have overall the same number of particles up there. And that vapor pressure, that pressure in that area above that liquid is what we're going to be calling the vapor pressure. The gases above a liquid in a sealed container is vapor pressure. Now, the vapor pressure, how many gas particles you end up with, is going to be dependent on a couple of things. And you can see that here on this next slide. The first thing it's going to be dependent on is how strong are your intermolecular forces. Okay, how strong are those intermolecular forces? Because, again, we said if we have a beaker and we have a stronger intermolecular force liquid, it's harder for the particles to evaporate. Okay, so if you have really strong, let's say this is strong intermolecular forces, you might only get 2 particles evaporating, when in comparison to a weak intermolecular forced liquid, like maybe this one has LDFs and maybe this one has hydrogen bonding forces. Over here, because they're weaker, more of them can overcome the attraction. You're going to get a lot more evaporation. If you get a lot more evaporation, you're going to end up with a much larger quantity of gas particles once dynamic equilibrium is achieved, once that ratio has been established. But you're going to have more particles exchanging. So in the strong one, you might only have 2 particles exchanging with 2 particles, whereas in this one, you're going to have 4 particles exchanging with 4 particles because you have a buildup of more particles up there. There's going to be more of them participating. So the weaker the intermolecular force, the higher the vapor pressure is going to be. And you can see here, the highlighted part's actually the opposite of that. So the stronger the intermolecular force, like this one here, the lower the vapor pressure is going to be, because you're not going to have as many particles. Vapor pressure is the pressure of the gas above the liquid, and if not as many as are evaporating, then that vapor pressure is going to be lower than it anticipated. Okay, so that's one factor. Another factor that can affect it, so let's say we have 2 beakers. They both have the same exact substance in them. Okay, so let's say they both have water in them, just for the sake of water. One of them is at a low temperature, and one of them is at a high temperature. That's going to affect their rate of evaporation as well. I want you to think for yourself. If I have hot water compared to cool water, which one evaporates more quickly? And I'm sure you said the hot one. Okay, the hot one will decrease how much liquid it has a lot faster than the other one, because we said in order for a particle to evaporate, it has to have enough energy. If you have a higher temperature, then you're giving more particles enough energy to overcome that phase. So in our high temperature situation, we're going to have lots of particles with enough energy to get out. Over here at the lower temperature, there's not going to be as many particles that are able to get out. So in high temperature, we're going to have a higher vapor pressure than when compared with the lower temperature. We'll have a lower vapor pressure. Okay, so the higher the temperature, the higher the vapor pressure, because more particles have enough energy to overcome those intermolecular forces. Okay, so there's a lot of things at work here, and it's all going to play into the next part of this, which is boiling point. So boiling point, and where water boils, anything boils, all has to do with that vapor pressure thing that we were just talking about. And you probably never, well, I know you never have thought about it this way, because you haven't really understood what vapor pressure was. And in order to understand boiling point, you have to understand vapor pressure. I mean, take a look at the definition. Definition of boiling point is a temperature at which a liquid's vapor pressure is equal to the atmospheric pressure. And my guess is you've never really even thought about the fact that atmospheric pressure plays into the boiling point of a substance. So I'm going to explain to you how this works. It's actually really cool, and I hope you feel at the end of this lesson like you really learned something that you definitely did not know before. So we're going to start with a pot. Yes, that is a pot. I'm sorry, I'm not the best artist. And our pot is on the stove, so it has heat. Yes, that is heat. And inside of our pot is water, squiggly line, universal symbol for water. And we have our pot on our stove. Okay, now you may be thinking immediately, okay, if we're doing vapor pressure, if something has to do with vapor pressure, you're going to have to put a lid on this pot, and that's not the case, and I will explain why, even though vapor pressure has to have a sealed container. And I want you to keep that in mind this whole time as we're doing our explanation. So before I've even put the heat on yet, please pretend the heat's not there yet, we have to think about what's acting upon the surface of this liquid. And you probably, again, don't really think about it because we're always exposed to the atmospheric pressure around us, but the atmosphere is in fact pushing down on the surface of this liquid. Okay, that is definitely occurring. We don't think about it because, again, it's around us all the time. We're going to pretend like we're at sea level, only for the sake of making it easier for us. So the pressure pushing down on our pot is 760 millimeters of mercury. Okay, so we start to heat up our pot of water. Now, again, look at the definition of boiling point. It says the temperature at which a liquid's vapor pressure is equal to the atmospheric pressure. So water is not going to boil until its vapor pressure is equal to the atmospheric pressure. So what does that mean? I don't, do I have to put a lid on this? Do I have to build up the gas pressure above the liquid to get this to happen? And the answer is no, because we all know we can put a pot of water on the stove without a lid and get it to boil. So here's what happens. I want you to pretend like we are little particles of liquids in here, okay? And we're all down here. We're all having a good old time. So I've got a lot of particles down here. We're all having a good old time, okay? Everything's hunky-dory. Then all of a sudden, because it starts getting heated up, I start to get a lot of energy. Okay, I'm getting more. Maybe you're not getting it, but I've got it. And we've got a temperature, of course, but I've got more energy than you do because temperature is an average of all those particles. So I've got all this extra energy, and I'm like, hey man, I don't want to be in here anymore. I don't want to be a liquid anymore. I want to be a gas. So I find another particle, okay? That particle also has a lot of energy. And I say, hey, let's do this. Let's break our intermolecular forces that are holding us together as a liquid, and let's push away from each other and become a gas. So we try it, okay? We try to form a bubble. You all know boiling water has bubbles, right? So we try to form a bubble. So you and I, we push against each other, and we try to push out to make a bubble form. Remember, I'm down here at the bottom of this liquid, okay? We try to make this bubble form down there. But you and I together, once we push away from each other and we have more space between us, and inside that bubble, by the way, is our sealed container. Okay, the bubble is the sealed container. It's completely enclosed by the water, right? So it's a sealed container. So you and I in this bubble, our bubble only has maybe, I don't know, 100 millimeters of pressure, mercury of pressure. So our sweet little bubble that we're trying to form with all the best intentions to leave is just going to be squashed by the 760 millimeters of mercury that's pushing down. My little bubble's only pushing out 100. 760 pushing down is literally going to smash it and turn it back into liquid and force us back into that liquid phase. So now I'm all bummed, and me and my particle buddy are bummed. We're like, yeah, we wanted out, but we're getting more energy. And we start to notice there's other people around us who are getting more energy too. So we get a bigger group of particles together, and they all have more than the average amount of kinetic energy too, and they're like, yes, we are out of here. And so all of us together, we push away from each other, we break those intermolecular forces because we have enough energy to get away from each other, and we make a bubble this time that has 450 millimeters of mercury of pressure. So we're doing much better. We have a lot more particles participating in our little Exodus plan, okay? But, once again, the atmosphere is pushing down 760. Our bubble is only pushing out 450, so even if we try to push out with 450 millimeters of pressure, the atmosphere squashes us and forces us back down. And so it's like, oh, man, closer. So we get more particles. Remember, there's more heat now, so more particles are going to have lots of energy. So I find an even bigger group of particles to come with me to form this bubble. And we make a bubble that is 720 millimeters of mercury of pressure, okay? And we try to push out to form this bubble that's going to have 720 millimeters of pressure, and what's the atmosphere going to do? Squash us once again. But we are almost there. We find a couple more particles because the heat's getting more now, okay? We find a couple more particles. By the way, if we're at sea level, we're just about approaching 100 degrees Celsius. And once we hit 100 degrees Celsius, we all get together and say, let's do this. We push away from each other. We break our intermolecular forces to form a gas, and we form a bubble that has a pressure of 760 millimeters of mercury. And guess what? It really forms this time because the atmosphere isn't stronger than us anymore, okay? Our bubble forms. We're all excited. What do we know happens to less dense things that are submerged in more dense things? They rise up, and our bubble comes up, pops at the top, and us gas particles run for good life, right? We're out of here. And that continues to happen in the rest of the liquid. Once that boiling point occurs, we've learned before that the temperature is going to hold at 100 degrees Celsius, and you're just going to get these groups, these pockets of particles that are going to overcome their intermolecular forces and become gases within the liquid, forming that bubble that can then rise out. But it doesn't happen if the pressure is not high enough, okay? The vapor pressure inside that bubble, that's our sealed container, is inside the bubble. The vapor pressure has to be equal to the atmospheric pressure. Now, those of you who like to bake, you may have noticed that a lot of times on a box, a baking box or something, it tells you high altitude directions. Okay, and the reason is because all of this stuff works the same, but if the pressure's different, then obviously there's going to be a different scenario of what occurs. For example, let's say we're not at sea level. Let's say we're somewhere where the pressure is 720 millimeters of mercury. that means our bubble would have formed earlier. Our bubble would have formed at a temperature less than 100 degrees Celsius, whatever temperature that happened at. I don't, we'd have to look it up to be able to tell. Actually, you know what? Let's look it up. There's a table down at the bottom of your paper. Okay, find over on the right-hand column, look for 720. Now, it's not exactly there. You can see millimeters of mercury pressure at 707 and then 733. So 720 would be right about in the middle of that. Right next to it, look at the temperature. So it would be right around 98.5 degrees Celsius. This one is going to boil at, and that's where it would hold at. So if you're at somewhere like Colorado or somewhere camping, your water doesn't boil at 100 degrees Celsius. Your food actually takes longer to cook when you're at high altitudes because the temperature won't be as high, and that's how food cooks. I don't know how many of you own a pressure cooker. Pressure cooker is the same concept. You are going to increase the pressure in order to make the water boil at a higher temperature, because when you live somewhere where the atmospheric pressure is significantly lower, your boiling point is significantly lower, and it makes it harder to cook food. You have to cook food for longer. That's why they have those directions on your boxes, is because it's going to take longer to be able to cook. Okay. Also on your paper, you'll find there's a definition that says normal boiling point. That word normal just simply means that you're at 1 atm. Okay, normal means 1 atm. So if somebody asks a question about normal boiling point, they're saying the boiling point at 1 atm. We'll see that a little bit more with the next lesson on phase diagrams. Okay, so if any part of this was confusing at all, definitely go back and re-listen to it. It will definitely help you sort of solidify these thoughts in your mind. But at this point, you should understand the concept of vapor pressure. Okay, you should understand that it has to be sealed container to be able to discuss vapor pressure. That's the pressure of the gas above a liquid. You should understand the ideas of evaporation and condensation, of course, and you should be able to understand the whole concept behind boiling and why something boils, how it boils. It's not just that it gets hot enough, because now you are smart enough to understand a lot more about the whole boiling process.